My name is Akul Goyal. This is joint work with Gong Wang and Adam Bates from University of Illinois and Michael Hahn from Wake Forest. So host intrusion detection systems, or HIDS, have had a long history in computer security, going back as far as 1972 with the release of the seminal paper, Computer Security Technology and Planning Study. Even Multics had its own HIDS, complete with a dashboard for security analysts. However, since the start of HIDS, they've always had a problem with adaptive attackers. Consider the classic example of Forest IDS. This is a sequence-based IDS that only trains on normal data. So given, for example, a audit stream, Forest IDS uses a fixed size window to create a database of unique tuples that it encounters. So at test time, if Forest IDS ever encounters a tuple it has never seen before, it raises an alert. In 2002, Wagner and Soto came with this idea that an attacker could space out their attacker objective so that they could evade detection. So what this kind of looks like is, if we look at the attacker objective of an open, write, and read, we see that the open, write, and read are not part of our normal database. However, an attacker could space out the attack by injecting analogous activity to create an event stream that looks like this. This event stream, when passed into Forest IDS, would not raise any flags. Notice that this event stream is similar to the event stream, is not similar to the event stream that Forest IDS was trained on. We refer to this problem as the minimal forward sequence problem. Essentially, because Forest is limited by its window size, the visibility of Forest is limited, and an attacker can take advantage of that. So modern day work in system auditing and machine learning have recast the problem of host intrusion detection system as a graph learning problem. So here we see an example of a Provenance graph, which details the system activity in a recent data set released by DARPA. The nodes in this graph are system entities, and the edges between them are system calls. Now, Provenance intrusion detection systems, or Prov-HIDSs, have shown great success in detecting attack behavior within these graphs. This is in part because these attacks have different structure than the behaviors that are occurring around. However, no work or little work has been done in investigating attackers that inject malicious or innocuous activity alongside their attack. So in this paper, we evaluate 5 state-of-the-art Provenance intrusion detection systems. We introduced 3 mimicry attacks that show we can abuse how these systems encode provenance graphs. And we show that our attack gadgets are able to achieve 100% success rate against all the systems. The key finding from our paper is that at present, state-of-the-art Provenance intrusion detection systems are just as susceptible to evasion as prior HIDS. For the brevity of this talk, we're going to focus on 2 of the Provenance intrusion detection systems, Unicorn and Prov Detector. So Unicorn is a Prov-IDS that deconstructs a graph by looking at the k-hop neighborhoods around each node in the graph. Take, for example, this Provenance graph. Here, we see a possible substructure could be the one-hop neighborhood around P1. Now, because Unicorn is a temporal-based system, it takes fixed time interval snapshots of the graph as it grows. So here, for example, in our Provenance graph, we see 3 different snapshots of the Provenance graph. Now, to compare against Provenance graphs of different sizes, Unicorn will normalize the counts of each of the substructures within the histogram. It then embeds these histograms into a d-dimensional embedding, which it compares against models of its training data. So Unicorn goes from this Provenance graph rich in information and scales it down to this d-dimensional embedding to represent it. And so by doing so, Unicorn is losing key information from the graph that allows for the attacker to evade detection. We refer to this attack as abused distributional graph encoding. And the way it works is by this first insight, where Unicorn normalizes the substructure counts in the histogram. This allows Unicorn to compare against graphs of different sizes. However, by normalizing the counts of different substructures, this inherently means that the normalized count is dependent on the counts of the substructures occurring around that substructure. What this boils down to is that an attacker who is looking to reduce the weight of attack substructures can simply upsample the number of benign substructures that occur within the graph. So what this looks like in practice is, let's consider an attacker that makes a move at timestamp 4. Here, we see that the attacker introduces the substructure A1, A2 with a normalized weight of 0.03. However, if the attacker also included benign substructures, we could see that the weight of the attack substructure is reduced from 0.03 to 0.02. Now, if the attacker is consistent in upsampling the number of benign substructures added to the provenance graph, the weight of the benign substructure can exponentially reduce to the point where it no longer has an impact over the classification of the graph. This allows for the attacker to evade detection. So in Prov Detector is another provenance-based intrusion detection system that breaks down provenance graph based on the paths that exist within it. Take, for example, the path P1, P3, F3. This is one substructure that would occur within the provenance graph. Instead of normalizing the counts of all the substructures within the provenance graph, Prov Detector assigns a rarity score. This rarity score is essentially the probability of that path occurring in benign data. The way it's calculated is by using a frequency table that measures how often an edge occurs in benign data. And so a path which contains a lot of edges that occur in the benign data has a lower rarity score. Now, Prov Detector down selects the graph and selects only the rarest paths to represent the graph. It embeds these paths and compares it against benign data. In our example here, we see that Prov Detectors selected the top 2 rarest paths, one of which includes the attack substructure. So similar to Unicorn, we see that Prov Detector takes a provenance graph rich in information and reduces it down to this d-dimensional embedding. Again, because Prov Detector is losing information, the attacker can take advantage. We refer to this attack as abusing downsampled graph encodings. So the first insight is that Prov Detector downselects the graph, looking at only the top n rarest paths within the provenance graph. This means, so because provenance graph are modeling system activity, there exists large variance in benign data. As a result, there naturally exists rare paths within benign data. So an attacker can insert these rare paths alongside their attack so that these attack paths are pushed down and no longer selected by Prov Detector. What this looks like is in the top, we see an unperturbed provenance graph where the attack substructure is correctly being identified. However, if the attacker was to include this path P1, P6, P6 to P6, which is a benign substructure, we can see that this benign substructure contains a high rarity score. So high that when it's included in the graph, it pushes the attack substructure from being selected, changing the classification of the graph. So for our paper, we focused on 2 different data sets, StreamSpot and the DARPA Transport Compute dataset. For this presentation, I'm just going to focus on one of those data sets, which is StreamSpot. This data set contains 100 unique attack graphs. So this shows our results for Unicorn. In this graph on the x-axis, we see the number of edges added by the attacker alongside the attack. And on the y-axis, we see the Jacardian distance. This is how Unicorn measures abnormality. So and the purple line represents the average distance to a benign cluster. So as the attacker adds more edges, we see that for all 100 graphs, it becomes looks more benign to Unicorn. to the point where at 40,000 edges, we are getting full evasion. Now, this may seem like a lot of additional edges added. However, if we look at the size of the graph produced, it's a small fraction of the average size of a benign graph. As a result, any statistical test used to detect these perturbations is non-trivial. We see a similar result with Prov detector. In Prov detector, again, we have the number of edges added in the thousands on the x-axis and the Euclidean distance, or how Prov detector measures abnormality, on the y-axis. Again, we see this really nice pattern where as more edges are added, the graphs look more and more benign. However, previously, unlike unicorn, Prov detector has this really nice step function because at each iteration of our attack, we add an additional benign path. And because Prov detector does the down selection, the number of edges required to evade is a lot less than the number of edges required against unicorn. We also experimented against some other Provenance intrusion detection systems. One of them was StreamSpot, where we see a similar result. Pagoda, where we see another similar result. And Sigil. And so for all of these Provenance intrusion detection systems, we see that as we add more edges, more benign substructures to the graph, they're more likely to evade detection. In our paper, some of the other things we have shown is that we can do this in a live experiment. So an attacker with limited knowledge of what the victim's benign behavior looks like can still carry out this attack. More importantly, these attacks that are conducted in the feature space where we're doing large transformations of graph, they can still be carried out in the problem space. We also compare against state-of-the-art adversarial machine learning algorithms and show that they are not efficient enough to create the needed number of perturbations to evade detection. We have many more experiments in the paper, and we invite interested listeners to go read it. So in this work so far, we have introduced 3 attack gadgets that target distinct properties of Provenance intrusion detection systems. We did not utilize adversarial machine learning in part to gain insights as to why current Provenance intrusion detection systems fail. However, if we had tried to, we would have seen that current systems are not able to scale to the number of perturbations needed to evade detection. So future work can look into developing an adversarial machine learning algorithm that utilizes some of the insights in this paper and correctly evade any kind of Provenance intrusion detection system. In conclusion, current Provenance intrusion detection systems lose critical information by applying out-of-the-box machine learning. Because they do whole graph classification, they must consider the entire graph, which results in the classification being dependent on the attacker's activity. This means that an active attacker can utilize benign behaviors alongside their attacks to mask their abnormality. Thank you for listening. We are now open to questions.
Hi, I'm Kathleen Fisher. I'm from DARPA, actually. And I wondered to what extent what you're talking, the work shows that this kind of approach is fundamentally flawed, that because the intrusion detection system is accessible to an adversary who can then study its behavior, the adversary will always be able to come up with a way to counter the system. Right now, it still requires hand expertise, as you say, that the machine learning algorithms out of the box aren't sufficient. What do you think the future trend is? Do you think that long-term, basically, an adversarial system will be able to take the intrusion detection system that's running and automatically engineer a way to work around it? So should we be fundamentally looking at a different kind of approach for securing systems? Thank you.
Yeah, that's a good question. I think that part of it is creating a system that is general to most intrusion detection systems. A lot of the attacks we've introduced are specific to the intrusion detection system that we've studied. We believe that it is possible for adversarial work to look at kind of a query and response system where it can query the intrusion detection system and kind of understand what's going on and create a general attack against it. So ideally it would come to a state where it's easily, you can apply any kind of ML-based algorithm and evade these systems, but we're not there right now.
Do you have a sense of what it would take to get there?
So, I think that right now, so first of all, most of these Provenance intrusion detection systems don't utilize any like gradients when they're learning. They're more like utilizing statistical techniques. And so a lot of the adversarial machine learning algorithms that are used against graphs, rely on these like any kind of gradients to learn some kind of attack. And so first of all, we'd have to use some kind of system that doesn't do that, which is like an RL-based algorithm. And current RL algorithms use like edges to create perturbation to the graph. Likely, you would have to go up in granularity and add like substructures. And so this would allow for something that's more efficient.
Thank you.
Hi, Alexander Boryaka from Boston University. Thank you for the interesting talk. Sort of to piggyback on the last question, like mimicry attacks against a system call-based IDS have been like shown for decades, as you mentioned. Do you think that going more granular, looking at system call arguments is a potential way forward, or is that also a non-starter?
That's a good question. I think that the point of this paper is to show that looking at, attackers can add benign activity alongside their attack to evade detection. So there is this idea of like, if we look at arguments, we could be able to better detect. In my opinion, I think that it still doesn't address the fundamental issue where attackers are inserting benign behavior alongside their attack. And so I think the main direction forward is to move away from kind of whole graph classification that a lot of current systems use and go deeper into the individual parts of a graph, for example, like nodes or edges.
Hi, Andrea Continella, University of Twente. Thanks for a very nice presentation. I was wondering whether you guys also looked at or evaluated the potential cost for attackers to implement these attacks, both in terms of effort, but I was wondering also in terms of time, right?
Right.
Does the attacker, need weeks to inject first benign events to then, evade detection and injecting malicious stuff? How does the time, play a role in these attacks?
It's a great question. So in the live experiment, we kind of measured these costs, and it really depends on the system that's occurring on. If it's like a high system that experiences a lot of activity, attacker can get away with a lot more perturbations quickly. But depending on the average system, this could take anywhere between days to a week or so. And I should actually show you. So we produced a statistical test where we had the average benign graph and the average attack graph. And so you can see that over the time period of an average benign graph, the attack seems hard to spot out. So yeah, it could take anywhere from days to a week to create this attack.
Hi, nice talk. So my question is, you mentioned attacker with limited knowledge can also successfully perform this kind of mimic attack. Right. I wonder why, because from your presentation, I think the attacker at least need to know this is an anomaly-based system. What if it's the defender have other types of provenance-based detection systems, say rule-based, graph matching-based, stuff like that? Right. Will this attack still be effective against those systems?
It's a good question. So yeah, the question was, how does this attack fare, if I understand correctly, how does the attack fare if the victim is also using other defenses outside of the graph IDS? Is that correct? So we consider a pretty isolated victim where they're just utilizing a graph IDS. We don't consider, other combinations of systems. In our paper, we do utilize the approach of like an ensemble where multiple graph IDSs are used. But no, we don't experiment with how does this attack work if there are multiple layers of security?